Good afternoon, everyone. I am Steph Nelson, your host. We will be going over what's new in the latest release of Test Lab 2406 in the environmental testing portion. Your presenter is Bill Flynn. Bill, would you like to introduce yourself?
Hi, Steph. Yeah, my name is Bill Flynn. I'm an application engineer located in Southern California.
All right, Bill, let's learn about what's new in 2406.
Okay, great. Thanks, Steph. This is the agenda for today and what's new in 24/6, specifically for environmental testing. So scheduled time storage in random control, abort trigger in online random reduction, virtual channels in random applications. People may be familiar with these virtual channels in other applications, but they're now available in our random control applications. Iterative gains in shock control, shape drive, and reverberant acoustic control. So scheduled time data storage in random control, we had a lot of requests that people wanted to record the time data for any test, really, any environmental test, but they can be quite long. And so it's not necessary to record the entire duration of a random control test, but you can now schedule certain periodic measurements and take little snippets of the entire time history of that test and store that to the database. And then you can check and see how things progressed. And there's also spectra associated with those time segments. That's all an option to do all this data storage. The benefit is to save disk space, of course, and facilitate analysis of time data while keeping safety of the full test recording. This is scheduled table, and this is nothing new here actually, but there's additional behind the scenes capability in that this was used before to specify when the measurements of the spectrums, average spectrums, are stored. You have an entire time test is a short one, just an example. At lower levels, you step up from -9 to -6, -3, and you do that for 10 seconds for equalization and tune the transfer function to match the reference spectrum. And then as you get up to full level, this is a 1-minute test, and then you can schedule periodic measurements with the 10-second offset. And then every 20 seconds, you're going to take 20 averages. That's periodic spectral averaging. And along with that, additional capability is that time data that's used for those channel averages, the spectral averages, is also stored in the database. So the periodic time data storage is synchronized with the spectral data. First of all, you use advanced time level table to program that, or you can use the automatic scheduling here, and it works the same way. So these equalization time, and you can specify a number of averages at those levels. And there's also in the online button box, you can initiate some manual averaging. So you can push the button to do the averaging, and it'll take 10 averages. And then that time data is also stored along with it. So you activate the recording, and then in this tab in the advanced control parameters, you have these extra additional features here in the new software. So you can record the entire test, which was what was available before, but now you can program measurements that correspond to this table over here. An option is to just not record the entire test, but to just take so many seconds before the end of test completes. So that's a new feature, and the way it looks in the software after you've completed a test, and this illustrates the data that you get. So as you're building up in these different levels, this is where I recorded the entire test, the time data, but also had periodic measurements. So these are recorded time segments 1, 2, and 3. There is also, as before, in these time segments, there's spectrums that are averaged and stored as part of the database. This full-time recording is an option. So that's the first added feature of 24/6. Then we got abort trigger in the online random reduction. Just to give it a little context first, this is a typical spacecraft scenario for testing where you have the main dedicated control system over here doing the controlling of the control channels and making sure that the average of those matches the required reference spectrum. And then as a supplementary system to all of that, to offload some of the burden of the control system, when you have a lot of channels, you can have a recording and reduction system that's recording the time data. But there's a lot of communication between these two systems, and that's provided through these synchronization lines. In the case of sign testing, there's a COLA signal that's output into the data reduction system, so it knows the instantaneous frequency and can process data as if it was part of the control system. But in random control, there's a status signal that comes out and is measured by the recording system to know what level the random control test is at. So there's communication between the two. And then there's an output over here on the recording system that is a abort signal, and that can be sent to this control system to signal an abort condition, and then that will initiate a shutdown of the controller to protect the spacecraft. And how it's set up in the software. So the new feature is this part right here. This is a abort signal that's coming out of the DAC output of output number 1, or whichever one you so choose on the recorder system. That abort signal is sent to the controller, so like a 1-volt DC signal, and that signal is monitored by the control system, and then on the control system you would set some abort conditions for that particular channel. Then on the control system, this is the standard capability where you have, of course, the signal going out to the amplifier and shaker, and then the status signal is going to the recording system and is set up as a status signal on the recorder system. So that's the hardware setup and a bit about how that new feature works. Another feature is the so-called virtual channels in random applications. So what you can do is in the channel setup, now this new additional capability to initiate and set up some of these virtual channels. Basically, a virtual channel is taking two physical channels, like maybe a couple control channels or a couple measurement channels, and doing something with those to, you can add them together, or there's other functions available like math functions to multiply those together or take the average between those two. You can also use all the capabilities in this function list here, and there's many more as you scroll down here, but there's things like filtering, there's integration. So you can see some of the list over here, but there's a longer list here. And you set those up here in the channel table. So in this case, as an example, I'm taking channel 1 and channel 2, the physical channels, and creating a virtual channel, and I can give it a name like VC for virtual channel 1 plus channel 2, and that's in a channel group of vibration. And one of the concepts of the TestLab controller, for example, is that these virtual channels are generated in the SCADA's hardware itself. So it generates time domain signals, and those time domain signals through the virtual channel processing are stored as just as if it was a regular channel or a physical channel, and that's stored as part of the time history throughput file as part of the database results from the test. These can be used for control and monitoring, and you can also set some abort capability on these different channels. They're in the time domain, so you can spectral process those and then use those for abort checking. So this is an example down here. So I've got channel 1 and channel 2, and if I create a virtual channel and add those together, I get this response down here in the time domain. Iterative gains in shot control, a bit of an obscure, maybe a kind of a feature that isn't used all that much, but especially for shock testing, the hydraulic actuators are used. And these can be nonlinear in the response. So as you're building up in level, the predictions can predict a DAC overload because of the nonlinear response of these actuators. These are used typically in low frequency, and this can be in multi-axis or single axis using hydraulic actuators. And these can be nonlinear, so you have to allow to overcome some of those predicted overloads if they're not real. And to allow that, you can interact with the DAC output gains, and that can help to overcome the error that comes up. The interface is, this is a new button here in the shock control for single and multi-axis shock. You can have this button called iterative gains, and then you can have different, like this is an example for a 2-shaker test, 2 hydraulic shakers where you have one in the vertical and one in the horizontal. So this is typical for earthquake applications where you have 2 actuators, hydraulic actuators with very high amplitude outputs. So that's iterative gains. in shock control. Then we have shape drive in reverberant acoustic control. Anyone using a acoustic chamber for acoustic control, you have a reference spectrum and you want to output those drives so that they, just like a control test using a shaker, you want to output the drives, in this case, octave bands. In random control, you adjust those in narrow bands, but in this case, we're adjusting the octave band responses and adjusting the drives output to accommodate that reference spectrum. Well, these rooms have kind of a signature, I'll call it, associated with it, where you output a certain voltage level to the amplifier and the speakers in a different frequency range, and they have a different output response spectrum at the different control mics. That's so-called signature or transfer function between the drive output, the voltages from the DAC output as a function of frequency, and then the response that you get back. And if you know this information ahead of time, you can use this to your advantage so that when it comes online, even at the lower levels, it's already got this pre-shaped signature drive output to accommodate a response spectrum. So a transfer function here that can generate this response output. So that's a new feature in the reverberant acoustic control system.
Well, I don't see any other questions on features and stuff you can do. So everything must have gone very well. Thank you, Bill, so much for your presentation.
Okay, thanks, Steph.
Bye, everyone.